Let's answer this question that I asked at the end of the previous part of the video lecture. So, we know that the E field is independent of what probe charge we use to measure it. And so, no matter whether we measure it with a positive probe charge or a negative probe charge, we should get the same answer. And so the field must point to the right. But you can be forgiven if you find that a little counterintuitive, because the definition of the field looks like if you reverse the sign of that probe charge, you should reverse the direction of that field. But follow the reasoning through. Let's think about this point P. When we say that with the positive probe charge we find that the E field points to the right, that tells you that when we put a positive probe charge at P, we find that there's a force acting to the right on it. And so now when we measure that, when we divide that force by the charge, we get an E field to the right. And it doesn't matter what's causing that E field. We don't know what's causing it. It could be positive charges over here, or negative charges over here, or both. I'm going to leave both, but remember, we don't actually know what's causing it. But now let's think about what happens when we use a negative probe charge. The negative probe charge will be attracted to the positive charges, or repelled from the negatives, or both. Either way, you get a force to the left. But now you divide that by that negative charge on the probe charge, and it flips the vector around and tells us once again that the E field is to the right. In the previous examples, we've been looking at cases where perhaps we don't know anything about the source charges, or maybe we just know that they're too complicated and we're brushing them under the carpet. But sometimes you know lots about the source charges. So let's look at the simplest case, when all you have is a point charge and you want to know about its field. So here's a point charge Q. And imagine that the whole region of space around it is modified by its presence. We say it is the source charge for a field. Now, if we're thinking about it as a source charge, then we're not interested in the motion of this charge Q. We are thinking of it as the source of a field which will affect the motion of other charges that we may be interested in. On the other hand, we can bring in a probe charge, and we would use it to map the field produced by Q. Now, it of course would produce its own field, but we're not interested in that. We're not interested in how this probe charge affects other charges. We're thinking of it as representative of charges moving through this region being affected by the charge capital Q. And so we might in fact be interested in the motion of this probe charge. So one way of thinking about this is that the charges which you want to think of as agents of forces are your source charges, and the charges that you want to think of as targets of forces are your probe charges. So now let's actually write down the E field due to this point charge capital Q. We know that the force that this charge exerts on our probe charge is going to be given by Coulomb's law, like so. And let's now think of our probe charge being at some arbitrary point P, and we're using it to probe what the value of the E field is there. And so we can work with our definition of the E field, that it is just the force on the probe charge divided by the probe charge's charge. And note that the way we've written the electrical force is all magnitude. And so let's only think about the magnitude of the E field. We know which way the direction is. If this capital Q is a positive charge, then we know, and the probe charge is also positive, we know the force is this way, and so the E field is this way. So we know how to find the direction. Let's just focus on the magnitude. So I've dropped the vector symbols and I'm saying magnitude of Q probe here. And so now we can just plug this expression for Fe into our definition of the E field, and so it's going to look like this. And notice that the probe charge cancels out on top and bottom, And we wind up with this. And notice how it is independent of what probe charge we use, just like we know has to happen. So this is now the E field due to the point charge Q, and this would exist everywhere in space around it, and it's a function of how far away we look. So to finish up this lecture and to help conceptualize E fields, I'm going to spend some time drawing them. We'll spend most of next lecture calculating them. So we know that a positive point charge, if we think of it as the source charge, is going to have an E field that points out away from it everywhere. Because if you put probe charges at these locations, the forces on them are going to be away from that source charge. And the other thing we know is that as you go farther away, the E field will drop off as 1 over r squared, like so. So it gets weaker and weaker the farther out you look. And just a matter of interpretation, when we draw these vectors, they're referring to the value of the field at their tails. So this vector here is talking about the value of the field here, not anywhere along here. We would have to draw more field vectors to show the value out there. And the last thing I'll do is just show a drawing of a field vector due to a pair of charges. So here you would have the E field due to this positive charge, which would point out away from it. And the point I've chosen is about the same distance from this negative charge, but the field vector due to it would point in towards it. And now you just do a vector addition, just like we did all the time in PHYS 1101, like so. And so you get a net field vector that would point, in this case, straight down like so. And you could go ahead and you could do this at all points. Well, it would take you an infinite amount of time to do all, but at many points around here to give an idea of the shape of the field.